In this video, I am going to introduce probability. I'm assuming most of this everyone's seen before. There are some definitions, there's some simple examples, there are a few rules you need to know, but basically I hope that all of this is familiar, although perhaps in the recesses of your mind. So, introduction to probability. First, the definition of probability. So the probability of an outcome is the proportion of times that the outcome would occur if we observed the random process an infinite number of times. Probabilities are always between 0 and 1 or 0% and 100%. So we have the law of large numbers, which is that as more observations are collected, the proportion, Pn hat, of occurrences with a particular outcome converges to the probability P of that outcome. Now there are a couple of things to remember in this law of large numbers. First, that as the number of observations get larger and larger and larger, Pn hat gets closer and closer to P. But second, the proportion is never exactly equal to P. So you've got to remember both of those things. So whenever you look at a proportion, it might be close to the probability, but it will never exactly equal that probability. Okay, so let's do an example. We're going to use rand between in Excel to simulate a 6-sided die toss 100 times. And we're going to compare the proportions that we observe from our 100 die tosses with the known probabilities. And of course, the known probabilities are 1/6 because it's a 6-sided die. We're going to assume each possibilities 1, 2, 3, 4, 5, 6 have equal probability, so the probabilities are 1/6. So in this spreadsheet, we are going to use rand between, so this will be our die toss. Die toss. I'll format that with heading 2. So we're going to use rand between 1, 6. So this function is going to give us the numbers 1, 2, 3, 4, 5, and 6 with equal probability. So rand between 1/6, that time we got 3. I'm going to format that as a calculation. And I'm going to copy this to all the cells between 2 and 101. I check in my bottom right corner down here. I've got 100, so I've done that correctly. So you can see the different numbers. If I re-evaluate my spreadsheet, I get different results. So I'm going to create a little table here with outcome, proportion, and probability. Let's format this correctly. So this will make heading 2. Make my columns wide enough to be able to read. The possible outcomes are 1, 2, 3, 4, 5, and 6. The probabilities are all 1/6. We'll format these as headings as well. So the probabilities are all 1/6. I'll write them as percentages and format them as outputs. The proportions, and I guess I should write these as percentages and also format these as outputs. The proportion, what we're going to do is we're going to go count if. So we're going to count how many of the die tosses have the particular outcome we're interested in, divided by 100. Oops, copied it a little too far down. Okay, so the outcomes, 1, 2, 3, 4, 5, 6. The proportions, I've used COUNTIF. The first parameter in COUNTIF are my die tosses, so there's 100 of those, comma, the outcome I'm interested in this case, 1. If I go to the next cell, you'll see it's cell D3. I locked the reference to the first parameter here so that A2 to A101 stays constant in all of these proportions. So those are my proportions of this set of die tosses with a particular outcome. The probabilities we know, each of them is 1/6. And you can observe that these proportions are never exactly 1/6. Sometimes they're higher, sometimes they're lower, and in fact, we can guarantee in this particular instance that they will never equal the probabilities, in part because the probabilities are 16.67, and because we have 100 observations, these proportions have to be whole numbers, 14, 19, 18, 17, and so on. So they'll never be exactly the same. But this gives you a sense of what's going on. If I changed the number of tosses from 100 to 1,000, my proportions will get closer. 100,000, even closer. 1,000,000, even closer, but they will never precisely equal 1/6. So let's go back. Few rules that we need to know. We need to know the general addition rule. So first off, disjoint outcomes. Two outcomes are called disjoint or mutually exclusive if they cannot both happen. So in the previous example of our die toss, getting a 1 is disjoint from getting a 2, is disjoint from getting a 3, 4, 5, and 6. All of these outcomes are disjoint because only one of them can happen. If we have two disjoint outcomes, then the probability that at least one of them occurs is given by the probability of the first one plus the probability of the second one. So the probability of A or B occurring, so at least one of them occurs, is the probability of A plus the probability of B. So what is the probability of rolling a 1 or a 3 on a 6-sided die? So let's say event A, outcome A is a 1, outcome B is a 3. We know the probability of A is 1/6, and the probability of B is 1/6, which means that the probability of A or B, one of them happening, is 1/6 plus 1/6, which is 1/3 or 33.33%. And this works because A and B are disjoint outcomes. Okay, the general addition rule, if we have two events and we don't know they're disjoint, then the probability of at least one of them occurring is probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Okay, so let's just think about this for a second. Within this probability, the probability of A certainly is the probability of A and B, right? Probability of A doesn't say anything about the probability of B, so sometimes when A occurs, so does B. So within probability of A is the probability of A and B. Within the probability of B is also the probability of A and B, which means that we've double counted the situation where A and B both occur, which is why we subtracted here. Okay, so let's do an example. Let's have two die rolls. So we're going to roll two dice. The first one comes up a 1, and the dice add up to 5. So these are our outcomes, and we want to know the probability that either the first or second outcome happens, and we want to know the probability that both happen. So either the first or the second, and the probability that both. So we're going to call this A and this B. We know the probability of A is 1/6. We've done that before. We don't quite know what the probability of B is, but we can work it out by just writing out the possible outcomes. So we have two dice. We can get a 1 on the first and a 4 on the second, a 2 on the first, a 3 on the second, a 3 on the first, 2 on the second, or 4 on the first, a 1 on the second. Okay, so those are the only possible outcomes for our two dice such that they add up to 5. So we have 4 possible outcomes that add up to 5. There are 36 total outcomes, so the probability of B is 4 out of 36, or 1/9. Okay, so now we need to think about, we know the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. So let's figure out the probability of A and B. Well, we can go look over this. We've enumerated our possible outcomes, and we can see that only one of them, this first one, has both A and B happening. So the probability of A and B is 1 out of 36, which means the probability of A or B is the probability of A, 1/6, plus the probability of B, 4/36, minus the probability of A and B, 1/36. So that's equal to 6/36 plus 4/36 minus 1/36, which is 6 plus 4 is 10, minus 1 is 9, so 9/36, which is 1/4, or 25%. So I'm using my general addition rule. The probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Okay, a probability distribution. A probability distribution is a list of possible outcomes with the corresponding probabilities such that the outcomes are disjoint, each probability is a probability, so it's between 0 and 1, and the probabilities must total to 1. So if we think about our die toss, we have possible outcomes, 1, 2, 3, 4, 5, 6. The probabilities of each of them is 1/6. So the outcomes are disjoint. We can only get one of these at a time. Each probability is between 0 and 1. Each of them is 1/6, 16.67%. And the probabilities, if we add this up, the probabilities total to 1. So this is a probability distribution. Complement of an event. The complement of an event A, denoted A raised to the C, so AC, represents all outcomes in the sample space that are not in A. So let's have a quick look. Let's say A is going to be the outcome 3, rolling our die. Then the complement of A is 1 or 2 or 4 or 5 or 6. Now, one thing you can note about a complement, first, A and its complement are disjoint. And A and its complement represent a probability distribution. Either A happens or AC happens. Probability of A happening, 1/6. Probability of AC, because these are all disjoint, probability of A, the complement of A happening, is 5/6. Each have probabilities between 0 and 1. They're disjoint, and the probabilities add up to 1. Independence. Two random processes are independent if knowing the outcome of one provides no useful information about the outcome of another. If A and B represent events from two different and independent processes, then the probability that both A and B occurs is the probability of A times the probability of B. So let's do an example. What is the probability that you roll a 1 twice in a row with a 6-sided die? Okay, so event A is rolling a 1 on the first die. And we'll have event B be a 1 on the second die. Now these are independent because whatever happens on the first die does not affect the second die. Okay, so these are independent. Probability of A we've seen before is 1/6. The probability of B we've seen before, also 1/6. Which means the probability of A and B occurring is 1/6 times 1/6, which is 1 out of 36. So that's our probability. So again, pretty small relative to each of these. So these are 16.67. These are quite a bit smaller.